All right, so if you were in class last week, we did discuss oblique incidence, and I tried to give you a feeling for the whole idea of how the definitions are made because it can be a bit confusing. So let's go back over that and then we'll look in more detail at the equations that govern both parallel and perpendicular polarization. So, as you recall, the plane of incidence is basically defined as the plane that contains the normal to the boundary between the two media and the direction of propagation of the incident wave. So, if you look here at this figure, here's the normal to the boundary, here's the vector k. So, the plane of incidence in this example is actually the plane that lies in the screen, or the xz plane. In this example, they say the plane of incidence is the xy plane, and that is incorrect. The plane of incidence is actually the xz plane. So please, when you're looking at these slides, make that correction. So a wave of arbitrary polarization, as we know, can basically be described as the superposition of two linearly polarized waves that are orthogonal. And in this example, that would mean that we would have one dimension of the electromagnetic field that would point out of the plane of incidence called perpendicular polarization, and we would have um, another polarization that would be perpendicular to that, which is referred to as parallel polarization because it's parallel to the plane of incidence. So once again, I apologize for the textbook error referring to the xy plane being the plane of incidence. In this example, the plane of incidence is actually the xz plane, so that the perpendicular polarization is perpendicular to the xz plane and the parallel polarization is parallel to the xz plane. So now let's look specifically at perpendicular polarization because it's a little bit easier to work with. So the perpendicularly polarized wave, the electric field, remember, is pointing out of the screen that you're viewing. And so we need to express the incident wave, and basically the direction of the field is in the y-hat direction, and the propagation is in this direction, x1. And so the H field then is perpendicular to that. So let me discuss their notation here. Basically, they're running two coordinate systems. One coordinate system is the coordinate system that is centered around the interface of the two media, medium 1 and medium 2. And so that coordinate system is shown right here at the center, where z is from left to right, x is vertical, and y is horizontal, pointing toward us. Then they're defining a second coordinate system that is the coordinate system with respect to the location of the perpendicularly polarized wave. So y is the same, it's coming out of the screen, but x has been rotated. So you can see that you have an x sub I and a y sub I, and that's been rotated because we're in the plane of the electric field. And by the way, okay, so anyway, the whole coordinate system has been rotated. So I also believe that there is, and so this y is the one that is pointing toward you, and actually um, this is actually z. So he's got a bunch of z sub I. So he's actually got a bunch of errors in this figure. So where he's indicating y sub I, that's actually should be z sub I. Where he's indicating y sub t, that actually should be z sub t. Now it doesn't make a difference in his final result. So we've got the electric field then that's pointing in the y-hat direction, and that's y-hat of the reference frame for medium 1 and medium 2, and then H is perpendicular to that. So what we have to figure out is basically a coordinate transformation. So this set of equations here, x sub I and y sub I, are a coordinate system transformation where we're going from the coordinates that are centered around the electric field to the coordinates that are centered around the boundary. And so with some trigonometry, x sub I, which is the direction of propagation, can be written as the sine of theta I plus z cosine of theta I, where this x and this z are actually vectors. They're unit vectors, so that's yet another error in this slide. This slide is filled with errors. So this is a unit vector, and this is a unit vector, and this is just a coordinate transformation to describe the direction of propagation. Then y can also be the y incident hat direction, which is I believe he should have labeled z if I'm following his coordinate system, where his y incident comes out of the screen. This then would actually be z sub I, and so you can see the whole coordinate plane is rotated by this angle 90 minus theta sub I. Okay, so this is your actually should be z sub I hat, and that gives then the direction of the H field. So the result is okay over here. So basically you have E pointed in the y hat direction, which is coming out of the screen. Here is the perpendicular part, the polarization. Here is the incident part. And here is the K dotted with the direction of propagation, which gives us K1 x sine theta 1 plus Z cosine theta 1. And then here is the H polarization, which is perpendicular to that, written in terms of the reference frame of the two materials, X, Y, and Z. This is not a cross product, this is multiplication. The cross product has already been taken by doing the cross product of the K vector with the E vector. So this is actually the direction of H, the direction of the H field. And then once again, here is the JKZ, the direction of propagation. So this can be very confusing. All right, now looking at the reflected wave, basically it is the same thing, only the angle changes, and as you know, the H field has to flip in order to satisfy um, the vector direction of K cross E. And then the transmitted wave, the same thing. E has the same direction and H has the same direction in this case. So the only difference in the unit vector notation is the direction in which the reflected H wave points. It's basically flipped. The tangential component of H has flipped. Okay, so we can then get expressions for the reflected wave and the transmitted wave, and these appear to be okay as well upon my inspection. So looks like no errors on this figure, other than he continues to mislabel his y here. It should be z. Okay, now then let's look at what happens when we apply the boundary conditions. So the tangential component of E is continuous, and fortunately here all of E is tangential because it lies in the y plane. So we basically just take the sum of incident and reflected E on the left-hand side and put that equal to E on the right-hand side. Tangential H is also continuous, and let Z go to 0. Tangential H is also continuous, so we take the x component only of H. So here is the x component of H on the left-hand side and the x component of Y on the right-hand side. And this is why it doesn't matter that he made his error and refers to this as Y incident instead of Z incident. That's why his answer comes out okay, but you just need to be aware that in the derivation that was an error. Okay, so here's the left-hand side being set equal to the right-hand side. So if you do a little manipulation and realize that this has to be true for all values of x, you come up with the following relationship for incident, reflected, and transmitted. And the same is true then the remaining terms. Once that's done, the remaining terms yield this equation here. So you can then solve simultaneously and get expressions for reflection and transmission coefficients. And basically that means that you get the following expressions. So these two equations under number 2, which are the E and H fields respectively, utilizing this equation relating K1, K2, and the signs of the respective angles. So you then come up with the following expression for reflection and transmission coefficients for perpendicular polarization. So you can see that they're very similar when you have normal incidence. The only difference is the indices of or the impedances are multiplied by the cosine of the incident transmitted and the incident and transmitted angles. So that is basically reflection and transmission of perpendicular polarization. So if we want to look at an example, coordinate system being the same, we have a plane wave that's radiated by a distant antenna, incident air upon a plane soil surface is equal 0. The electric field is given as follows. So you can see we have an X and a Z component to the propagation. So this is coming in at an oblique angle. The soil medium can be lossless, relative permittivity of 4. We're asked to determine K1, K2, and the incident angle, expression for the total fields in air and in the soil, and an average power density carried by the wave that's traveling in soil. So let's look then at this example. The first thing we do is we convert this into a phasor. So it's in the y-hat direction. Here is the phasor showing the direction in which the wave is traveling. We know that K1, X1, where X1 is in the frame of the wave, is equal to this expression in the exponent. So if we set K1, X1 equal to the expression in the exponent, we also know from our coordinate transformation that K1, X1 is K1 X sine theta plus K1 Z cosine theta. And so K1 sine theta is equal to pi, K1 cosine theta is equal to 1.73. We can divide equation 1 by equation 2, coming up with an expression for the tangent of theta, and determine that theta is 30 degrees. And we can square both equations and add them together, eliminating sine and cosine, and then that gives k is equal to 2 pi. So the wavelength in medium 1, which is air, is 2 pi over K1, which is 1 meter. Wavelength in medium 2, which is soil, if we take the relative epsilon, we'll come up with 0.5 meter. So that then allows us to calculate K2, which is 2 pi over lambda 2, which is 4 pi. So we now have K1 and K2. Now, given that the incident angle is 30 degrees, we can find the transmission angle by using the relationship between theta transmitted and theta incident, K1 and K2, and we get that the transmission angle is 14.5 degrees. So this is basically Snell's law here. All right, so now epsilon 1 is equal to epsilon naught, and epsilon 2 is equal to 4 epsilon naught. We can then plug in for the transmission and reflection coefficients and get the following. So then the total electric field in medium 1 is the incident and the reflected. So we take our incident, and then we take our incident and multiply it by gamma. And notice the sign SIGN on Z cosine theta is reversed because this one is moving in the backwards direction at the oblique angle still, but in the backwards direction. We then can substitute in the sine of theta I and the cosine of theta I, so that we get an expression that looks like this. So we basically have the forward moving wave with an amplitude of 100. the reverse moving wave with an amplitude of 38, both pointing in the y-hat direction. We can then convert that to an instantaneous field by adding in the j omega t. Okay, so in medium 2, we basically take the incident and we multiply by the transmission coefficient, and then theta changes to theta transmitted. So that changes then the what's in the exponent, and the amplitude becomes 62. And likewise, we can put that in the time domain by adding in the j omega t. So in medium 2, eta 2 is basically eta naught over the square root of epsilon relative 2, which is 120 pi, divided by the square root of 4, which is 60 pi. And so we can use the average power from the Poynting vector, that it is E transmitted squared over 2 eta 2, plugging in the amplitude for E, plugging in 2 eta 2, we get 10.2 watts per meter squared. So you can see once again that his little error in expressing the vectors in terms of one another in this particular example is irrelevant, because we're looking at E and the final result ends up being okay.